Transformations of functions affecting the x value. A recommendation: if you have not watched the video on transformations affecting the y value, I suggest you go back and watch that now, because we will reference some of the ideas we learned in this video to help us understand the transformations affecting the x. A quick reminder that a transformation is a change in the function, such as an up, down, left, or right movement, a vertical or horizontal stretch, or a flip over either the y or the x axis. In the last video, we looked at a general function y equals f of x, and then we put some extra variables, some numbers, a, b, c, and d, and came up with another equation which is going to give us all the different possible transformations of our function f of x, at least in the stuff that we're going to be doing. We talked about how a and d affect the output, or the y's, because they are outside of the parentheses. And b and c affect the input because they're inside the parentheses. But notice, in our original function, we have y equals f of x, right? So the x's, whatever inside the parentheses, is the input. Whatever's outside is the output. We also talked about how if you understand how one function moves or is transformed, you understand all functions. So for now, we're going to start with a parabola again. We're going to change from it just a bit. And we're going to look at the following transformation. X plus c. What happens when we add or subtract something to the x inside parentheses? To understand what's going on, the y of things, let's go back to our original function y equals x squared. And let's look at this point right here. Really, if I know how that one point moves, I understand how the rest of the graph moves. Because everything that's inside parentheses is going to affect the x value, meaning some sort of left or right movement or stretch or whatever is going on. So looking at this point here, we know that this is the lowest point on the graph. We know that y must be non-negative, greater than or equal to 0, because anything squared is greater than or equal to 0. Now, when does the function reach its lowest point? Well, it reaches its very lowest point, its minimum value, when x equals 0. How does that help us? Let's consider the graph y equals x minus 2 all squared. Once again, we have something that is squared, which means the y value must be non-negative. You can't square something and get a negative value, at least not with real numbers. Now, what value of x is going to give us our lowest point? That is, what value of x will make y equal 0? We can do a lot of work, but I think we can see just by looking that this will occur when x equals 2. So the only thing that happened in our graph was a movement 2 spaces to the right. Because that's what this is saying. Nothing else changed except I get my new lowest value of y when x equals 2. So when we had x minus 2 in parentheses, we shifted to the right 2 spaces. Some people teach us or think of this as doing the opposite, and maybe that helps us understand, meaning when we have x minus 2, we went positive 2. You can think of that being opposite, but it's not. The math is doing what it's supposed to do. Let's take a look at another one here. Let's consider y equals x plus 3 squared. Anything squared means our y's will be non-negative. The very lowest value of y will be 0. And we want to find what value of x makes our lowest point, our vertex if you would, or our minimum at y equals 0. I bet you've already figured it out. You've taken the time and you realize this occurs when x equals negative 3. Because negative 3 plus 3 squared equals 0, and then 0 squared is 0. So even though it says x plus 3, we're going to go minus 3, or 3 to the left, 1, 2, 3, and then redraw our graph. It looks like it's doing the opposite, but it's doing exactly what it's supposed to do. Let's move on and look at our next transformation. But we're going to have to change functions here when we do the following. We're going to look now at what happens when we multiply some number by x. Notice again that we're still affecting the input because we're inside the parentheses. So we're going to have some sort of left or right fix, if you would. Let's go back and talk about our parabolas when we did the following. When we did y equals a times, say, x squared. Where this right here be y equals 1x squared. And then we did some problems where he said, let's let y equal, say, 2x squared. And we determined what happened to our graph, which was the following. Some people call it a vertical stretch. I say the y's are growing twice as quickly. At the same x as the original, our y will be twice as big. We're getting to the y's twice as quickly. So what if we do f of 2x? Now, you don't have to know or be familiar with the sine graph. That's really from if you've taken trig before, but really this is a good graph, a good function to work with when we're trying to understand what's going on over here. And so if you're not familiar with the graph, you can trust me, this is what it looks like, or you don't have to. You might want to go to something such as Desmos to help us understand kind of fixes. And that's certainly what I do when I'm in class. We would go into Desmos and put sliders in to change these different values here and just see what happens very quickly. But to understand what's happening, what do you think the sine of 2x will look like? Well, if 2 times f of x was a vertical stretch, because it's affecting the output, then f of 2x we could think of as some sort of horizontal stretch. We already talked about this a little bit, but how does it stretch the graph? What do you think? What do you think f of 2x will look like? And you have two choices. Either it's going to look something like this, or it's going to look something like this. Which do you think it is? Do you think it's the red? It gets stretched out farther, or does it get compressed like the blue? And the answer is, it's the blue. Now, why is that? Well, one way to understand it is to plug a bunch of points in and see that this is actually what happens. That's probably the best way to understand it, but we might not be familiar with sine graph and plugging points in. Another higher level kind of way of thinking about this is when we did the following, y equals 2x squared, for a given x, we got to the y twice as quickly. So here, at a given y, we're getting to the x 2 times as quickly. You might want to stop the video and just take a little time to think about what that means. But it does indeed give the blue graph. Now, what do you think the red graph will be? That is, what do you think the equation of the red graph is? If you said f of 1/2 x, you are correct. Because at a given y value, we're getting to x's 1/2 as quickly. So once again, when we're dealing with inputs, it almost seems like we're doing the opposite of what we should. But we're not. The math is doing what it's supposed to do. Now, let's give ourselves a little bit of space here. And let's see what happens when we make things negative. And once again, we want to compare what we're doing to what we learned when we're doing stretchers or things that affect the y. Now I'm going to go back to our parabola because this transformation works very well with parabolas. Y equals x squared. And like we said, what happens when we do y equals negative x squared? Well, with negative x squared, it said, let's take all the y values. We're going to keep the x, but the y values will now become negative. And I'm drawing it dashed like this just to show us that it's a different graph. Of course, it should be connected like that. All right, well, what about if we're going to do f of negative x? Well, f of negative x says, kind of at a higher level thinking, just like with the y's, it said with any x, you leave it but make the y value negative. Here it says leave the y's alone and make the x value negative. So we're actually going to have to switch graphs to understand this one as well. And let's do the following. Let's do the square root of x instead. So we'll say f of x is the square root of x. What does f of negative x look like? Well, we could plot it, or we could write it out as the square root of negative x. But what's happening? Just as we said, at any given y value, the y value is not going to change, but the x value will now become negative. So all the y values stay the same, but the x values switch. Like that. And that would be f of negative x. So let's take a look at one more problem. Let's do kind of a general case. And let's draw a nice function composed of, say, some line segments. We're not going to get too fancy with it. Just something like that. So here's f of x. And let's draw the following function. Let's do f of negative 2x. So when we're drawing transformations, especially ones where there are multiple transformations, I highly recommend that you do things in pieces and by order of operations. Now, they're both multiplications. Really, I have negative 1 times x and 2 times x, which I'm going to separate out. But since they're both multiplications, you can do either one that you want. So I will do f of negative x first, and let's make that one red. F of negative x says leave the y values alone, but now make your x values negative. That is, if that didn't make sense the first time, right here we had the point 2, 2. So I still have the y value of 2. But the x value now becomes negative 2. And this point here was the point 3, 0. So when I said 3, I of course meant 4. So the y value is still the same. It's still 0. But the x value becomes negative. And once more, the original point was 6, negative 2. So the y value will remain, but the x value becomes negative. So this is, and I'll rewrite in the correct color, this is f of negative x. So the red is f of negative x. Now let's do f of negative 2x. Once again, the y values stay the same. But now we're getting to those particular y values twice as quickly. So we'll still have the point 0, 0. We'll still have the y value of 2, but it doesn't take us a full negative 2 to get there. It only takes us half of that, a negative 1. That is, we're getting to that x value twice as quickly. And then we get to the next x value, that is, instead of negative 4 being our x, we get there twice as quickly, that is negative 2, 0. And our final one, we have the same y value of negative 2, but instead of taking a full negative 6 on the x, we get to the x's twice as quickly. That is, it only takes us negative 3 to get out there. And so our blue graph is f of negative 2x. So recall that when you're doing transformations, and this is one of the most important things I want you to get out of this. Note that if you know how a transformation affects one function or any function, you know how it affects all functions. Where inside the parentheses is affecting the input, the x is somehow something horizontal. And outside the parentheses is affecting the output, the y's, something vertical.